Okay, hello everyone. So today again I am going to extend a few of the problems so you have a better practice on it, right? And let us start. So this part again, so we are dealing with the topic that is calculus of variation, which is my third lecture, and we started with problems, right? So let me write here that is given a variational problem of the form integral that is I of x over the definite integral x1 to x1 to x2, and the given functional of the form f is a function of x, y and y prime into dx, to which I need to find the solution curve that is y of x1. And if I substitute this value, for which y1 is equal to y of x1 and y2 is equal to y of x2, will be the solution curve, right? So let me have another problem, and that is my sixth problem, that is find the curve on which the functional that is integration from that is 0 to 1 y1 y prime square plus 12xy is that is into dx with y of 0 is equal to 0 and y of 1 is equal to 1 can be determined. Okay, so I need to find the output of this. So this is a general interpretation. Fine. Yes. So yesterday the usual procedure what we have said. So solution. How do we write the solution? Right. Now here that is f, x, y and y prime, right, which is equal to that is this given function, it is y1 square that is y prime square plus 12x y. Then next you should always have the habit of writing this particular thing. Then also we know that by Euler's equation we have. And why do we that is to solve the variational problems, what we do, we make use of Euler's equation. That is, it is given by dou f by dou y minus that is d by dx of, and it is dou f by that is dou y prime, and which is equal to 0. So this is your equation 2. You can consider this as equation 1, okay, and this is as equation 2. So this is equation 1. So what you need to do is, see here, so you need to find the value of dou f by dou y, since so it is independent, so you have all the values, right? So dou f by dou y, okay, make use of this. So here so dou f by dou y is equal to, so here it turns out to be that is 12x, and one more thing, that is dou f by dou y prime, so that is dou f by dou y prime is equal to 2y prime. Again what you have also that is d by dx of dou f by dou y prime, which is equal to this. I can write it as C here. This is d by dx of, what is the value of dou f by dou y prime? It is 2y prime, which is equal to, so this in fact I can write it as 2 d by dx of y dash is nothing but it is dy by dx. This is for your simplification purpose I am writing. At any instant you can write it directly, need not calculate it, okay, which is equal to 2, this I can write as 2y double prime. Now substituting the above values, this given above values in equation 2, that is in 2 we have, that is dou f by dou y, it is 12x minus, so d by dx of dou f by dou y prime, it is 2y prime equal to 0, right? Now this equation, okay, so this is correct. Now what I do is, so I can divide it by 2 and I can rewrite this particular given equation, that is which is equal to, if I take this to the other side, so this turns out to be y double prime, which is equal to, or if I divide it by 2, this turns out to be 6x, right? So and which implies this is nothing but this is d square y by dx square equal to 6x. Now this is a differential equation, fine. So there arises a differential equation, so how to evaluate this? So what I do is I integrate this, therefore on integrating, that is we have, if I integrate this, this turns out to be, that is dy by dx, which is equal to, that is 3x plus c. Then again integrating we have, okay, if I integrate this, so definitely fine. So what finally I want my answer to be, that is in this particular manner, that is y is equal to y of x. So if I again integrate this, I have y is equal to, that is 3x square by 2 plus cx plus c1, and this turns out to be your output. So is it not of the form y is equal to y of x? In fact this turns out to be your solution if you can take common terms out. So it is as simple, fine. Okay, now what are the things? Okay, so that is my solution, but I also have that is condition, that is y of 0 is equal to 0 and y of 1 is equal to 1. So value of here, what I do is now taking the conditions, now y of 0 is equal to 0 and y of 1 is equal to 1. So here, which implies this is nothing but y is equal to 0, or you can write it as, that is x equal to 0, y is equal to 0, and this is x equal to 1 and y is equal to 1. Now when you substitute this to get the values of, that is this if you take that is c1 and this if you take c2, right? So here if you substitute the value, that is x equal to 0 and y is equal to 0 over here in this given equation. So first what I'll do is I'll substitute this particular values. So this is y is equal to 0, so this is 0, which is equal to, that is 3, x is 0, so I do not write it. So c1 x is 0, I do not write it, so therefore c2 is equal to 0. Therefore one of the value is, that is c2 is equal to 0. Now if I take this particular value and if I take y is equal to 1, which is equal to, so x value is 1, so this turns out to be 3 by 2 plus, and here it is 1, and this sorry, here it is C1, right, and value of C2 is, it is 0. Therefore this turns out to be, therefore value of C1 is equal to, that is 1 minus 3 by 2. So C1 is equal to, that is 2 minus 3, that is C1 is equal to, that is minus 1 by 2. Fine. So therefore the final output, I missed somewhere. Let me check. Yes, student. Yeah, I hope I am extremely sorry that here I am into a dilemma. I take my words back. So when I am integrating this, so here, that's the reason. Here it is that is x square, that is 1 2, and here it is 2, so it becomes 3x square, right? And then here again if I integrate this, this becomes y, so x plus this becomes x cube by 3. I am extremely sorry, I take my words back. Then again here this 3 and this 3 gets cancelled, so it is y is equal to x cube. So here it is y is equal to x cube. So you answer this, y is equal to x cube plus c1x plus c2. This turns out to be your output, and then substituting the value, that is x equal to 0 comma y is equal to 0, and that is x equal to 1 comma y is equal to 1. Now here therefore when I am taking this particular values and substituting so to get the values of C1 and C2, so this is 0, which is equal to, so x is 0, so value of C2 is obviously 0, right? And what I'll do is I will take x equal to 1 and y is equal to 1. So here it is 1, which is equal to, that is 1 plus value of C2 is 0, so value of x is 1, so this turns out to be C1, so which implies, right, so this one and this one get cancelled, that is C1 is also 0, so the value of C1 and C2 are 0. Therefore your final output will be, I'll be writing here, so therefore the solution curve is, that is y is equal to, that is when I substitute C1 equal to 0, C2 is equal to 0, y is equal to x cube. So this turns out to be a solution. So please make correction. Here I have taken here I had taken, that is 3x. It is not 3x, it is 3x square, because I am integrating it, right? Fine, and that turns out to be a solution. Now so that is your required curve. Let me have another problem. Find the extremal of the functional that is over the limit, that is x1 to x2, that is y1 square minus y2 plus 2y sec x dx, right? Okay, fine. So let me write the solution. So same procedure, same method of evaluation. So here again you write the given functional x, y and y prime is equal to y1 square minus that is y prime square, it is dy by dx the whole square minus y square plus 2y sec x, right? So also we know that by Euler's equation, that is from Euler's equation. So I make use of this. So let me consider this as my equation 1, right? Or you can consider this as your equation 1, okay, to which I need to find the solution in the form of y is equal to y of x, okay, and then I make use of this Euler's equation. Now the first thing is shadow and rub. It is as simple. So what is dou f by dou y? So it is, here it is, see, y prime y square 2y sec x. So here this turns out to be, that is minus 2y plus 2 sec x when I am differentiating partially with respect to y. Now what is dou f by dou y prime? So dou f by dou y prime is, which is equal to 2y prime. Now if I take this, and that is d by dx of dou f by dou y prime. So this I can write it as, which is equal to, this is d by, if I take this 2 outside and if I write d by dx of, this is y prime. So which in fact I can write it as 2y double prime, or in short you can directly write this, or that is d by dx of, that is dy by dx. This y prime is nothing but that is dy by dx, right? So which is equal to, that is 2y double prime. Fine. Now substituting the above values in equation 2. So what are the values of dou f by dou y? It is minus 2y plus 2 sec x, right? And dou f by dou y prime, it was 2y prime, and if I take d by dx of dou f by dou y prime, it will be, that is 2y prime. Now if I substitute in equation 2, right, so if I substitute this in equation 2, so my answer turns out to be minus 2y plus 2 sec x minus 2y double prime equal to 0. So since everywhere there is 2, so I am divided by 2, and therefore on rewriting it, so if I rewrite this, I get y double prime plus y equal to, that is sec x, right? Now see here, this is a differential, okay, this I can write it as, which is equal to, that is d square plus 1 y equal to sec x. Now this is a second order differential, ordinary differential equation. This is my f of d and this is my sec x. So see here, in your previous classes you will have evaluated, that is homogeneous, that is non-homogeneous ordinary differential equation of second order, taking, that is right hand side being a function. So for standard function like e raised to x, some polynomial, sine, cos, you will have certain rules and techniques for that. But here this time the right hand side value is sec x. So what I do is, to evaluate such type of equation, right, I make use of, that is method of so we need to apply, so equation of this type, that is the given function is not a standard function, therefore I can make use of one of the method known as, that is a method of variation of parameters. So we need to apply method of variation of parameters, okay. So if I make use of, to solve the ordinary differential equation, but before to that, that is I will take the differential equation, so the complementary, I will take its complementary function, so method of variation of parameter, therefore I will take its auxiliary equation. So the auxiliary equation is m square plus 1 equal to 0, m is equal to, that is plus or minus I. So this I get imaginary roots, therefore the complementary function is C1 cos x plus C2 sin x. Now what I do is I take my solution, okay. So that is if I take the complementary solution, and let me assume, so let y is equal to, that is a cos x plus b sin x be the solution. So let me consider, that is y is equal to a cos x plus, let me check, yeah. So for the given differential equation, that is ordinary differential equation, so I consider my solution to be in the form of, that is y is equal to a cos x, which is a standard one. So for any second order differential equation, so what I do, y is equal to a cos x plus b sin x be the solution, where a and b are what, are functions of x to be determined. Okay, so where okay, so what I do is now, okay, let me rub this. Let me check whether I have given the correct formula or no. Okay, now to that particular solution where a and b are functions of x to be determined, so and if and y1 and y2 are solutions of the given ordinary differential equation, then which is homogeneous, then we have, that is the given polynomial, okay, in terms of y equal to 0. Therefore since a and b are functions of x, therefore value of a is given by minus integration of, it is divided by, that is phi of x dx into w, yeah, and this is y2, right, since I need to find the solution, that is the value of a and value of b, and value of b is equal to, that is integration of y1, that is phi of x divided by w dx. So this w is nothing but the Wronskian, same as the case of what you have taken in a few concepts, you make use of Jacobians, and same is the case we make use of this now Wronskian. Now the purpose of this Wronskian is to bring the given solution in terms of its linear independency, right. So how to calculate this Wronskian? So here Wronskian is calculated by, you write all the y, so you write 1 2 1 2, so here 1 prime you take and here 1 prime you take, right. So Wronskian is always calculated by, that is y1 y2 prime minus, that is y1 y1 prime y2. Now here phi of x is equal to, that is sec x, right. Now what I do is, let me map this. Now So if I assume my solution, that is C1 y1x, so what I do is, so this solution I am assuming it to be in the form of, that is C1 y1x plus C2 y2x. So if I take now y1 is equal to cos x and y2 is equal to, that is sin x, and that is the reason I am taking Wronskian to bring an output. From the use of Wronskian is that we can get an output in terms of its linear independency. Okay, so that is y1. So this, so if I take y1 prime, it turns out to be that is minus sin x, and y2 prime, it turns out to be cos x. Now if I want to calculate this Wronskian, so what does the Wronskian says? It says that, see here it is y1, so y1 is cos x, and here it is y2 prime is cos x. So obviously this turns out to be, that is cos square x. Okay, and here it is minus, right? Here it is minus, so this becomes plus. Here it is sin square x. Okay, so the value of Wronskian is 1. Therefore I need to find the value of a, where a and b are the functions of x, right? So here, therefore I will write it here. Therefore a is equal to minus, here it is, what is the value of y2? It is sin x. Okay, sin that is sin x, phi of x is sec x into dx, and Wronskian is 1, so I do not write it. Okay, same is the case if you take b is equal to, that is integration of, so y1 value is cos x. Okay, and here it is sec x dx, so which is equal to, that is a is equal to minus, so this sin x and this sec x, I can write it as 1 by cos, so this becomes sin by cos, it becomes tan x dx. Okay, and here value of b, this sec x and this cos x, so it is integration of 1 dx, right? So here it turns out to be, value of a is minus log of tan, that is sec x plus c 1 you can take, and here you can write it as, that is x plus c2. So the value of a is minus log sec x plus c1, and value of b is x plus c2. Therefore what I do is, to which I substitute the value of that is a and b, where is, yeah, so which I have assumed, so the solution to be in this particular manner. So y is equal to a cos x plus b sin x, so I substitute the value of a and b over there. Yeah, therefore on substituting the value of a and b, okay, you can number this equation. So is that you can write this equation 3, and you can write on substituting the value of a and b in 3. So here, therefore y is equal to, value of a is minus log sec x, okay, plus c1, okay, and then it is cos x plus value of b is, my value of b is x plus c2 and sin x, and this turns out to be a output. And in much more precise manner, if you want to write, you can just write it, and that turns out to be a solution. So y is equal to minus log sec x plus c1 cos x plus x plus c2 into sin x, and this is your solution, right? So that is the reason I said while solving the problems of calculus of variation, first thing is you should observe, you should make your to solve that problems, you should make use of Euler's equation. Only based on that particular that is Euler's equation, you will arise with a differential ordinary differential equation, So what you do is you make use of already available methods which you have already studied in your previous classes. So make use of it and bring the answer in the form of, that is, y is equal to y of x. So that was all about how to solve that is variational problems, right? So few of the problems, okay, homework problems we have also given you, right? So let us move on to, that is, application part, which is as important. So let us see. So this is over. So applications of calculus of variation. So what we do is we'll have the problems such as some problems on geodesics, some problems on catenary, and some problems on that is hanging chain problem, and some problems on that is a very interesting problem, that is bronchistron problem, which is a very interesting problem, and you can prepare seminar also on that on some at some time, right? So first application I will be taking as, that is, geodesic. So what exactly is this geodesic? So geodesic is nothing but the least length of the curve, you can say, between any 2 points. Now suppose if I am having 2 points, that is A and this is my point B. So what is the least length of curve? See here, I can reach this point in this manner, I can reach this point in this manner, I can reach in this manner, I can reach in this manner. So what is the least length of the curve which I need to determine? So that is nothing but, that is the geodesic. Okay, fine. So write the definition. Let me write it in a proper manner. So I need to find given two arbitrary points A and B on a surface. So this surface is S. So you can consider this blackboard as your surface and take 2 points, okay, and comma there exist number of curves on S. So if this blackboard is my surface, and if I take any 2 points, okay, so you can take this part, you can take this part and then come to B, you can take any part, okay. Now of these curves, now if I am taking this A and B, and if I take the curves from here to here, from here to here, from here to here, right, anywhere, which is the least one, okay. So the least one, so the least path between these two extremes is called as geodesic, right, and which is also in the form of y of x. Fine. So let us have the problem. In my very first class I have given the plus, okay, in my very first class I have given an example of, what do you say, functional, right? So let me have that description for you. Yeah. So let us start with the problem, and then in between I shall explain you. prove that the shortest distance between 2 points in a plane is along a straight line. Or this given question, whenever you hear the word geodesic, it is the least distance traced or covered on the surface between two extremities, that is 2 points, right? As I said, if you take 2 points on this surface of this blackboard, and if you can trace from A to B, how many ways? There are infinite number of ways you can move till B or B to A, right? So which is the least one? So the least curve is its geodesic. Okay, so that is the reason. So this problem is based on it's a geodesic problem. So here, see, the question is, prove that the shortest distance between 2 points in a plane is along it is always a straight line, right? Or the same question they might ask you, that is prove that the geodesic on a plane is a straight line, right? Or the same question they might ask you, prove that the shortest distance between 2 points is a straight line, right? So see here, now when I'm saying that the shortest distance between 2 points in a plane is along a straight line, so what will be your output it in the form? So your output will be in the form of, that is y is equal to mx plus c, which is a straight line. Or if you take that is in your earlier classes, that is plus 2 and 12th standard also, you have equation of a line passing through 2 points, that is you have an equation, that is slope intercept form, that is what is that, one more, slope intercept form, 2 point form, and that is point form, right? So finally you need to get an output that is a straight line, right? So fine. Now what I do is, I will write the description of this problem in a proper manner. You can write it in your own words, there is no problem. So here, solution, let A is equal to x1, y1 and B is equal to, that is x2, y2 be the two extremities, and S be the length of the arc, and S be the length of the arc joining these points. So what I'll do is, I will take this coordinate, I will take the point A and I will take the point B, and I will take a curve like this, right? So the coordinate points of this is x1 and y1, and the coordinate points of this is x2 and y2. This is my x and this is my y. Then S, the length of the arc, is always given by, that is it is over the limit, that is x1 to x2, and that is some part, that is ds, which is equal to, that is integration of x1 x2, and it is square root of 1 plus y1 prime square into dx, right? Or this I can write it as integration of x1 x2 square root of 1 plus dy by dx the whole square into dx, right? So let me consider that as you can take either the first equation or the second equation. Fine. Yeah. So here, how this equation has arisen, let me tell you. Many of the students will ask, sir, how did you get this particular, that is, and in my very first example, this given equation, either you consider this equation or this equation, it is one and same. So how did you get this value? So see here, so it is, what is that concept? Derivative of an arc length. Suppose this is my curve, and what I do is, this is x-axis and this is y-axis. So this is my surface, that is curve, okay, that is s be the length of the curve. I take some part of this curve. Suppose if I take this part of this curve and some part of x, okay, I will take this part and this part. So this is some part of x, so this is dx. This is some part of, this is along y, this is some part of y, this is dy. This is some part of s, so it is ds, right? So what I do is, so therefore by using Pythagoras theorem, so this is just for your explanation purpose. So this is ds square, okay, that is dx square, that is dx square and dy square. So this is ds is equal to, that is ds is equal to, that is square root of dx square plus dy square. Fine. Now also we know that, but see here, the slope dy by dx is nothing but f dash of x, okay. So this is dy is equal to f dash of x into dx. I can write it in this manner. So the value of dy is f dash of x into dx, to which I will substitute here. Therefore ds is equal to, that is dx square plus this f dash of x, I can write it as f dash of x, okay, square, and this is dx square, because I am substituting the value of dy over here, okay. So here it is ds is equal to, that is square root of this dx square and this dx square, I take it outside, so this becomes 1 plus f dash of x square into dx, which in turn I can write it as, that is square root of 1 plus f dash of x is nothing but, that is y, right? So this is nothing but y prime square into dx, and that is the reason I am taking this. So if you take some part of this, okay, and evaluate, so the distance, that is derivative of an arc length, that is over any given limiting values of x1 and x2, it is some ds, and the value of, that is derivative of an arc length, is always given by, that is the shortest distance, it is minimum, right? So square root of 1 plus y prime square into dx, and this is the explanation of it, okay. Now so let me consider this as equation 1. Now to this problem, what I do is, I do not take my usual Euler's equation. What I do this time, I write, that is, I have given certain forms of Euler's equation which are also useful to solve, that is variational problems. So this time what I do, if you can check, if write this instructions, if S satisfies the Euler's equation, then it will be minimum, right? And for my convenient purpose, I take this particular equation, that is dou f by dou y minus sorry, I am extremely sorry. Yeah, not for my that is okay, dou f by dou y into d by dx of, that is dou f by dou y prime equal to 0. So I make use of this Euler's equation, and that is the usual way. Fine. So here my equation, I am taking this equation. So here it turns out to be, that is dou f by dou y, and that is, so here dou f by, sorry, here dou f by dou y is equal to 0, and dou f by, see here, dou y prime is equal to, so here you have, that is square root of 1 plus y1 prime square. So this is square root of so which implies this is 1 upon 2 root 1 plus y1 square into dou by dou x of, that is y1 square, that is it is composite function, so which is equal to, that is 1 upon, so this composite function with respect to, that is y, it is not x, y prime, so this becomes 2y prime divided by 2 square root of 1 plus y1 prime square. So this 2 and this 2 gets cancelled, so I am having my output as y prime into square root of 1 plus y1 square. Fine. Yes, therefore substituting the value, therefore substituting the above value, in equation, you can take this as equation 2, value in equation 2. So equation 2, dou f by dou y, it is 0 minus, here it is d by dx of, what is the value of dou f by dou y prime? It is y prime into, that is square root of 1 plus y1 square equal to 0. Fine. Now, so once if you have this particular equation, so what you do on rewriting this, yeah, it is a differential equation, yeah, so it is d by dx of, that is y prime square root of y prime divided by square root of 1 plus y1 square equal to 0. Now to this equation, which implies, therefore on integrating we have here, if I integrate this, this turns out to be, that is y prime divided by, and that is square root of 1 plus y1 square is equal to c, yeah, which implies, now this is y prime, yeah, which is equal to c into, that is square root of, this is y, that is 1 plus y1 square. Now if I square this value, which implies this becomes y1 square, that is y prime square, which is equal to c square inside the bracket 1 plus y1 square. Fine. Now which implies, see here, y1 square, which is equal to c square plus, that is c square y1 square, right, which implies So which implies, so this equation, if I take from here and this constant, right, so this turns out to be, which implies here y1 square minus c square y1 square, which is equal to, that is c square, which implies here y1 square inside the bracket 1 minus c square, which is equal to c square, fine, which implies y1 prime square, which is equal to c square by 1 minus that is 1 minus c square. This in turn, see, simplification you can do it on in your own way. There is no restriction for you people. This is just an explanation, because in some textbook they have given you directly. Okay, so this y1 square is equal to m square I can write, because 1 square, so everything is square. So if you write, so which implies again this square, that square get cancelled, so y1 is equal to m. Now this is nothing but y prime is nothing but d by, that is dy by dx. So therefore on integrating we have, so on integrating what do we have, that is we have that is y is equal to, which is so integration of m, if you take, it becomes mx plus c. So this is your solution, and which is a straight line, and that is what we have proved. So first thing is what type of application or the question is being asked. So it is a geodesic problem wherein you need to find the least curve or the shortest distance, which is always a straight line. Need not be in few cases. With respect to some application, there is nothing like Bronchestone problem is one such problem, wherein with respect to certain parameters like weight, density, and gravity, okay, so there is a problem wherein the shortest distance covered by the body is not the straight line, but it is an elevation, like it is a curve. So that problem is very important and also interesting. So this is y is equal to mx plus c. Now if you substitute also in another way, if you have been given some points like now, when y1 is equal to y of x1 and y2 is equal to y of x2. Now remember these points, if you take, there are also one more method, that is here, if p is equal to x1 y1, so the solution, sorry, so if I take this value, that is in therefore we have, that is y1 is equal to, that is mx1 plus c, and y2 is equal to mx2 plus c, right. Now if you subtract y2 and this equation and this, so I get y2 minus y1 is equal to m x2 minus x1, right, which implies, so this slope, so m is nothing but the slope, m is equal to, this is y2 minus y1 divided by that is x2 minus x1. So this is the slope which you are getting after substituting this. Also in your +2 classes, so what you do is, also we know that by slope point form, also we know that by slope, that is point form, okay. So the slope point form says that you have a coordinate, that is x and y, so you have some point p, some point a, any point, that is x1 y1, and some point on this curve, that is p is equal to x comma y. So what is the point form? So that is y minus y1 is equal to m x minus x1. and if you take any of the point over this and you know that okay, that is the slope of this, so you can in general write, making use of this. In few textbook this problem is being extended and you have got the solution till here. If you write the solution till here also it is okay, and if you write explain us by taking that is x1 and x2 as its values and substitute and show us that the slope is y2 minus y1 divided by x2 minus x1, and substitute in a slope point form. This is a general form. So y minus y1 is equal to m x minus x1. So here it is y minus y1 which is equal to, I will take this slope, anyways it is a slope, so this is y2 minus y1 divided by x2 minus x1 into that is x minus x1. So this is also your solution, which is a straight line. So we have proved it by all the means. So whatever you take a geodesic problem, and if you want to find the shortest distance between, see if this is a surface and I am standing on this surface, I want to trace some gentleman or some miss over there. So what will be, I will not go from this side, I will always choose the straight line which is the least, right? So that will be my the curve from myself to you will be a geodesic, right? So this is what we have proved, and it is always a straight line. So here we have proved that is y is equal to mx plus c, and also by taking the points that is x1 and x2 and making use of that is slope point form and then substituting in it, so we have the straight line again, right? So one more example. Okay, I think it is time up. So one more example application part, I'll do it tomorrow, and then it will be followed by Z transformation class, right? Thank you very much.